What's up, everybody? Today we are going to talk about very important subject, SOS, sum of squares programming. Okay, for example, I think you know at least a little bit about LP, linear programming, right? QP, quadratic programming, right? And then maybe QP, quadratic constraint, quadratic programming, right? And SOCP, right? Second order con programming. I mean, programming here means you can change the word programming and optimization in that context, okay? And SOS programming, right, is one of those optimization tools, okay? And I feel like SOS programming or SOS optimization tools are gaining popularity, right? And maybe one of the reasons the computers are getting stronger, right? And another reason is I think more people are now aware that you can use SOS programming techniques to solve really, I don't want to say directly hard, but yeah, you can say hard and maybe non-convex, right? Yeah, sure. You can, relax SOS programming techniques to relax your non-convex optimization problems. Okay, and the premise is really important here, right? I mean, being able to at least having some tractable way to solve your non-convex optimization problem is a really, it basically is answer to all the questions, right? Let's not go philosophical. Okay, so we will use SOS programming, and to learn about, we are going to use first of all YALMIP, right? And for as an STP solver, you can use STP-T3 or MOSEK. I just started using MOSEK, right? I was using STP-T3. Okay, it's not important. Today we are going to look at 3 important small toy, right, problems, but I think it will be very enlightening for you, right? Okay, first problem is this: determine if the given this polynomial, right, x and y are the indeterminants. Okay, this is the terminology used here. Okay, and second problem will be minimize a polynomial. We will have a non-convex or a polynomial having multiple minimal local points, right? Minimize a polynomial, right? And the third problem will be we will look at a polynomial. Let me write it down. Polynomial optimization. What does it mean? Polynomial optimization is this: the thing that you minimize is a polynomial, okay, in x, for example, and you have inequality and equality constraints that are also polynomial. And I guess people use semi-algebraic sets for that type of set, right? This is the set that you take your decision variables, right? Or your decision variables should be in. Okay, all right. 3 problems. We will use how SOS programming can help us solve those problems, right? Okay, let's, wait a sec. Okay, let's look at directly Matlab codes, right? Go back to Matlab screen, control up. Okay, all right. So here it says install MOSEK or STP-T3 or any other STP solver in that matter, right? It wouldn't matter a bit. And YALMIP, okay, YALMIP is an optimization tool, all right. And okay, it is basically like 13 lines of code or something, right? Okay, and this is our polynomial, right? And we want to check whether it is SOS, sum of squares polynomial, right? Okay, why would we want to know that? Because SOS if a polynomial is an SOS, that will indicate it would, it wouldn't have any, for any x and y, it wouldn't have any negative as a result of that x and y. Okay, it will never be negative. Okay, and later we will talk about a polynomial being positive. Okay, and let's go quickly. This is our polynomial. X and y STPR, right? X and y are indeterminates. Okay, all right. And monolist is the command in YALMIP, right? And it basically generates all the monomials. Okay, all right. Maybe s display z. Okay, let me just run that section. Okay, and wait a sec. Maybe I should do something like this. Let me run this. Okay, I just generated the monomial vector, right? Let's look at them. All right, so first of all, degree p is 4. Why 4? Because the maximum degree is 4, right? This polynomial, the degree of that polynomial is 4. Okay, and why would we want to divide by 2? Because we will use this equation, right? We will use this equation. Okay, and we have talked about that previously, right? And I will again talk about that to make it clear, right? All right, so let's generate this Q matrix. Okay, let's generate this P SOS matrix. Okay, all right, let's look at this line. It says that now we have P source expression. Okay, what is the expression? It has Q terms that we want to find. Okay, right, and we want to find PSOS, right? We want to find PSOS such that it is basically equal to this, right? And also it can be written or expressed as this term where this Q matrix is a symmetric semi-positive definite. Okay, all right, let's run this. Okay, successfully solved, right? And I'm using Mosek. Okay, successfully solved, and it would indicate that this line successfully solved. We were able to solve this problem. So in a way, or what would that indicate? We were able to find P source expression such that it can be expressed in this form where z is the monomial vector, okay, and Q is a matrix, symmetric, semi-positive, definite matrix. Okay, what again? What does all that mean? Means that this P polynomial is a sum of squares polynomial. Okay, and you can consider this P polynomial being symmetric, no, not symmetric, semi-positive definite polynomial, because it can take for some x and y, for some x and y, it can take 0, right? You just cannot directly say P is a positive polynomial in that at this stage, right? But P is at least positive semi-definite. P greater than or equal to 0. Okay. For any x and y values. Alright. Alright. That's the, and let's look at the Q. Alright. Q matrix is this, and we can look at the eigen values. Okay. Again, by the way, this can happen, but it's again 0, right? That type of numerical, I guess, yeah, numerical issues, but at the end these are zeros. Okay, and all of the eigenvalues of Q, they are either positive or 0, meaning Q is positive semi-definite. Okay, all right, that was the first problem, right? So let's go back to Tablet. Okay, wait a sec, made a mistake again. Come on. Okay, what's our second problem? Let's look at that. Let me check my notes. Right. Okay, now we are going to minimize a polynomial. Okay, so wait a sec, let me get this over here. Okay, let me here. Problem 2, minimize the polynomial. Okay, what is the problem? Minimize using x, right? Minimize this polynomial. Okay, and just to visualize, our polynomial can be something like this. Okay, but it's an unconstrained problem, right? Okay, and we want to find basically this point. Okay, but again, this is not a convex optimization problem, because this polynomial is not convex, right? It is not have a ball shape structure. Okay, and we can express this problem as minimize, or rather, wait a sec, rather maximize gamma. Okay, such that e of x minus gamma is SOS. Okay, at first it may look strange to you, right? I mean, it certainly did for me, right? Okay, and basically we will subtract some gamma value, right? And if the resulting polynomial is SOS, right? Wait a sec. Okay, this is no problem. And we just subtracted some gamma. Okay, and maybe gamma is 0.1. Okay, and we look at this, we just subtracted. Okay, so this is p of x minus gamma. Okay, we are looking at this right now. Okay, and we look at this polynomial, and is it SOS? Yes. So what does it mean? We can subtract, or we can increase gamma again, right? Let's make it 0.2. Okay, again look at it. Is this maybe now I should make it like this, like used to be here. Maybe let me get another color. This is for gamma equals 0.1 and this is for gamma equals 0.2. Okay, and again look at the polynomial. Is this SOS? Okay, so increase gamma again, right? And till this polynomial is no longer SOS, right? And this is a bisection problem, right? And maximize gamma such that this polynomial is SOS. Okay, all right. This is basically it, right? This is basically covers our problem. And let me change the screen. I'm making this mistake all the time. Okay, all right. First of all, you can just download this document. What I'm explaining here in this video, right? You can just find everything that I explain in this documentation. Okay, for example, this is SOS problems, YALMIP MATLAB, and this is problem 1, the problem that we looked at, right? And this is the Matlab codes, right? Okay, and here this is the problem 2. Okay, and all right, find the minimum value of the given polynomial, and it is called 6-hump camel. This function is called 6-hump camel function because it has many local minimums. Okay, and it kind of looks like that. All right, and the answer to that question is minus 1.0316. Okay, and let's try to again, here is the Matlab codes. Okay, let's try to, you can download this documentation. Just check the GitHub link down in the description section below. Okay, here this was problem, yeah, this is problem 2. Okay, this is that 6-hump camel function. Okay, let's run this section. All right, again we are constructing our monomial vector. Okay, monomial terms. All right, and again we can, maybe let me get this, we can again maybe run this section, and then we can look at the monomial vectors. Here we can see, right, degree over 2, right? Okay, why degree over 2? Because this is the structure that we are trying to express our polynomial, right? And look at it again, it has quadratic structure, right? It is like the, in the Liopanov of function problems, x transpose p x, right? If p is a positive definite matrix, you would know that x transpose p x term is positive, right? You would know that positive definite function. All right, and again look at this, the maximum degree, right? Maximum degree in z's maximum degree must be this term, right? Half the maximum degree of the p. Okay, because we are going to square that basically. Okay, again these are the monomial terms, right? Okay, and again I call it gamma, but again you can call it of course t. All right, and this basically explains or express, yeah, what we just talk about. Okay, maybe I should get back to here. Okay. Maximize P. Okay. Such that P minus P is SOS. Right? And we can indicate this as equals P SOS. This is another polynomial. Okay. And then we can also, build on that. Instead of saying maximize, we can say minimize minus T. Okay. And P of X minus T equals, instead of saying again P SOS polynomial, we can say Z monomial terms, Q matrix, and again Z, right? And where this equality holds and Q is positive semi-definite matrix. Okay. And yeah, this is basically the problem, right? Here again we are expressing this term as SOS, P underscore SOS. Okay. And this is our second constraint, this equality constraint. All right. The coefficients of those polynomials being equal is first constraint, and Q being, positive semi-definite is second constraint, and minus T is our objective term. Okay. All right. So this is basically, right? And now we can run this, and the answer is this. Okay, volume. The T term is the minimum. Okay. Okay. And now let's look at the second problem. Okay. This was third problem. This was the second problem, right? And again, the answer is correct. Okay, let's look at the third problem. Here, yeah, this is called polynomial optimization. Of course, it's incredibly general. This way of indicating or stating a problem is very general optimization problem. Okay. And all right, maybe we should look at this. Let me get rid of that. One sec. Okay. Yeah, this is our problem, right? And to solve that problem, what you need to do is the following, right? It is similar to the Lagrange multiplier subject. Okay. And I mean, basically, this is the term, or yeah, this is the term. At first, it will not make sense, right? But if you are familiar with Lagrange multipliers, multipliers, right? And you use them a lot, this will come as a, sensible, I guess, manipulation, right? And again, we are expressing the problem, optimization problem, as a bisection problem, right? And again, minus gamma, we again use that. Okay. And this is the equality, and the fact that this equality exists or something, right? This is called positive Stirling-Satz, right? Of course, I butchered that word, right? And let's look at this. Let's look at, maybe it would makes more sense. Okay, this is our problem. All right, and we are manipulating that problem, right? And this is the problem that we are looking at right now. And we just made some manipulations, right? Okay. And this is the equality that we need to impose on the problem. Okay. And where we are defining, like in the Lagrange multiplier case, we are introducing new variables, right? And we are introducing new variables. But in the Lagrange multiplier, these were some numbers, right? They were some numbers, but the quote-unquote variables that we introduce here are polynomials. Okay. And sigma polynomials are SOS, right? And lambda polynomials are just polynomials. We don't need to have any SOS constraint on them. Okay. And basically this is, I mean, if you don't want to spend much time on that, you can just memorize this, transition, right? If you have some problem, you can just indicate or express the problem given in that form. Okay. Where in this problem you need to find gamma, right? Gamma, and then sigma polynomials, where each sigma polynomial is a SOS. Okay, we have SOS constraint. Okay, and also you need to find lambda polynomials, where they're just polynomials, and you have this equality constraint. Okay. All right, so this is it, and this is a very important problem, right? This is as general as you can get, and this is where SOS tools shine, right? And I understand if your problem becomes, I mean, this basically is all the optimization problems, right? Yeah. But I'm not saying, of course you can change the problem in that form, okay? But I'm not saying it is easy to solve this problem, right? However, you have some tractable means of solving this problem now, right? Okay, right? So let's look at our problem, right? And yeah, this is the problem. Maybe I should put this in, thumbnail or something. Okay, here our f of x is this term, okay? And g1 and g2 functions, and h1 and h2 functions. Okay. All right. And you can find this problem. I took it from SOS 400 manual PDF page 40. Okay. So let's get back to, and again here the Matlab codes, right? Related Matlab codes. A little bit longer, but it's like 35 lines of codes or something, right? Not that much. And again, this is, to be honest, this is not a high dimensional problem, right? However, this is not a trivial problem. This is a non-convex optimization problem, right? Not trivial, right? Okay. And I'm not saying all convex optimization problems are trivial. Okay, let's look at the third problem. Okay. And yeah, it's going to be a little bit hard for you to see, I guess. Hopefully not. Let me make it larger. Come on. Okay. Wait a sec. Maybe I should do something like this. Yeah, I'm going to make it smaller. I feel like you are able to see that, but wait a sec. Is there a way for me to make it smaller? make this smaller, I guess. I mean, you can get this code again from that documentation, right? The same code. Okay, wait a sec. Maybe I should make it larger. Okay, come on. Okay, I think you are able to see that. Hopefully. Alright. Okay. Alright. Line by line. Okay. Here, the first line is okay, clearing the all variables. And here we are just defining, initiating our indeterminates. Okay. And this is the term to be minimized. And these are the inequality constraints. And these are the equality constraints. Alright. And degree, we are basically, yeah, when I talk about SOS tools making non-convex problems to be tractable, I meant that basically, right? And you can just increase that degree, right? If you are able to solve that, okay, you are able to solve that for your maximum degree being equal to 6, right? But also, if you are not able to solve that, you can increase that for 7, and then again you can try to solve that. If not, okay, increase it by 1, right? And but in each increase, right, your problem becomes higher dimension of, right? Of course, it is not a good thing, but positive side, if you look at the positive side of it, at least you have some type of tractable way of solving a non-convex and really hard problem. Okay. All right. So this is it basically. And here we have 3 sigma terms. Okay. Sigma 0, sigma 1, and sigma 2. Maybe I should again show you the wait a sec, where is that? Just give me 1 minute. Okay, continuing. And this is the problem basically. This is our, let's call it the general formula here. This is our general formula, right? And this term, this expression is we are focusing on right now. And by using this expression, by using this form equality, I guess, or yeah, let's call it identity, right? And this is our problem at hand. Okay, and this is we are using this identity for this specific problem, right? And here we need to find gamma, okay, gamma, sigma 1, sigma 2, sigma 1 2, or you can say sigma 3, right? It's like the naming convention. And lambda 1 and lambda 2. So basically we need to find 1 number and 5 polynomials, 3 of which are SOS. Okay. And it also says plus ... it goes like this. But since we have only 2 inequality constraints, right, we can just, you know, delete that part. Okay, delete that part for this problem, by the way. Okay, all right, so this is our problem. We need to solve this. All right, let's get back to MATLAB. Okay, again, what do we have? We have sigma 1, and you are, I guess, at this stage familiar with this type of sigma 1 polynomial. sigma 1 or sigma polynomials being SOS, how can we express that? First of all, we need to have monomial vector, okay, and then monomial terms times, and our Q matrix, and by using this quadratic expression, and also this is a matrix, right? And each entry is a number, okay, and we need to find those numbers, right, such that this is positive and or symmetric, positive semi-definite, okay. All right, so these three lines basically as display functions are just to visualize, being able to see the explicitly our monomial vectors, okay. So step 1, you first generate your monomial list, okay, and then you define your matrix. For each polynomial you have a matrix, right? For each polynomial that you need to find, for each SOS polynomial that you need to find, you have some corresponding monomial vector, okay, vector of monomials, and then you have a matrix, okay, and then you construct your SOS. This is decision variable, okay. All right, so this, whenever you have some type of source polynomial decision variable, these three lines that you use for that, okay. And again, the same identical thing for sigma 1, sigma 2, and also sigma 1 2, or you can just call sigma 3 or something, right? It's the naming thing. And whenever you have source polynomial, again, right, a source polynomial decision variable, right, source polynomial that you need to find, right, you use those three lines to I guess initiate your source polynomial, okay. And here recall we have also lambda 1 and lambda 2 polynomials. Notice they are not source polynomials, they are just polynomials, okay. And you can initiate your polynomial decision variable or object by using this line, okay. And it gives you this, and generate a polynomial where maximum degree is 6, okay, and the indeterminate terms are x1 and x2, okay, and the name of that polynomial is lambda 1, okay. The corresponding, for each polynomial and also SOS polynomial, you have some corresponding monomial list, okay, and also you have some coefficients of that, okay. All right, and the same thing you can do, you do for lambda 2, okay. All right, and this part is the critical part. And again, you define your gamma or t here, and this expression looks long and complicated, but if you look at it carefully, this is exactly this expression. This is exactly this expression, okay. All right, so don't get thrown off by that, okay. And here is a critical part. Recall we have sigma 0, sigma 1, sigma 2, and sigma 1 2 we have 4 SOS polynomials, and each SOS polynomials that we need to find, right, and there's corresponding matrix, and these matrices must be positive semi-definite, okay. And we are just imposing that constraint on the statement of the problem, okay. And here again mosaic, and this is a bisection problem, right. We could also use bisection comments in that for this second problem, but I mean, we didn't, right? But we could use that. Okay. All right. So let's run this. Okay. Let's do something like this. Do something like this, and let's run it. Okay. It's gonna take like 15 seconds or something. You see, it's yeah, it's running by section. Okay, it says successfully solved, and the answer. What's the answer? The answer is t, or the gamma, right? We call it the gamma. So minimum of this term is 1.3911. Okay, and the answer is correct. If you look at the source tools 400 manual PDF page 40, you will see that. Okay, and here the Matlab codes, the corresponding Matlab codes, you can download this documentation from the GitHub page, right? The link is in the description down below. All right, and thanks for watching.